Every time.
I signed up for it,
And it's just not working.
I redid it, and then I got this. That's literally what I just did. So I have to reconnect and do it all over.
This prevents me from signing in the class.
I need more money back.
Yeah, exactly.
Get you the key card to keep the key card doesn't even work.
The key card doesn't even belong to the University of Arizona.
All right. Good evening, everyone. Let's go ahead and get started. Today, again, it's the scheduled lecture. I'm not sure how much time this will take, but we'll get to the end, and then whatever time is remaining, we'll spend it on projects. But before I start, today is Tuesday, and it was some deliverable for the project. Do you guys want to present, or do you want to do it on Thursday? 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 Okay, Thursday.
Half of our team.
Huh?
We're missing half of our team today.
Okay. All right. So let's do on Thursday again. What am I looking for Thursday? I'm just looking for an update, right? Just show me like a little bit MVB, how it is heading. Just want to make sure all groups are kind of progressing towards the end. All right. Okay. So let's do today. So in the previous class or the one before also, we looked at algorithms. You guys looked at sorting algorithms on Saturday. Today our focus is going to be data structures. They kind of go hand in hand together. If you are taking a computer science class, usually the course is called Data Structures and Algorithms. That's what it's called. So basically it has two parts to it. One is algorithm and one is data structures. So I'll go through when we get to the data structure part what those are, and once we get into that data structures, you will see that you actually recognize some of them, right? We have been using some of those, but just not by the name data structures. Okay. And then big O. Big O is a really, really big thing when it comes to interviews and our algorithms. I'll talk about what big O is, and usually you will see if you're sitting in an interview and they ask you a question and you quote it out, the follow-up question would be, hey, what's the big O for this? Usually. Not optimization. They'll ask, what is the big O for this? Right? So you have to tell what is the complexity. I'll talk about what big O is and then how to kind of come to some intelligent answer that you can throw out, right? Usually it's like 3 or 4 possible scenarios and, one of them you'll get it right. I've done that. I'm like, is it this? No. Is it this? Maybe this. All right. Yeah, it is this. All right, we'll try to come to see and maybe with a more intelligible guess. Okay, so we'll do this on Thursday. The project one. Let's see. Let's skip to this. All right. So you guys were looked at algorithms. You guys saw some sorting algorithms. Probably started a little bit okay, and towards the end, there were some more complex ones. Like quick sort is kind of complex. Just understanding quick sort is complex. Forget about the coding part. But it kind of gets pretty scary pretty quickly. And we'll take a look at some of those. It's not going to be as complex as this, but some of the concepts are more important over here. That will kind of help you go through some of them. Okay. This is all good. All right, these two again. I'll be honest. I haven't read any of these books, but they've been recommended. So if for those of you who are kind of would like to learn more by books, these are 2 recommended ones. The good thing about these are they are in JavaScript. Usually what you find is you'll find books written in Java or C# or kind of those languages, but these are kind of written with JavaScript code. Right, so some of the things that you guys have learned in this class would kind of be applicable over here, and all the algorithms that we are seeing can be written in any language. Okay, if you Google just like quick sort and then put the language name, you will see the code comes up, right? So This is geared toward JavaScript, so kind of makes more sense to you guys. Okay. All right. So when it comes to algorithms, right? It comes to efficiency, like how efficient your algorithm is, right? That has been always been the target. That's why you see we start with some like basic algorithm, like which uses like two for loops when we are trying to sort an array or we are trying to do binary search without the binary search, right? If then evidently then somebody else comes out with a different algorithm, right? It's a progression. But what is the goal? The goal has always been efficiency, right? How efficient my algorithm is. Now, what do you mean when we talk about efficiency? Okay, it means fewer steps. Okay. Now, fewer step doesn't mean less amount of code. That's not what it means. It means that your algorithm is going to take less number of steps compared to some other algorithm. That's how you measure the efficiency. Okay. Always remember the number of steps, the less the number of steps, the more efficient the algorithm is. Okay, you remember we did binary search versus just looping, going through each element. Binary search, it was half in like first attempt and half in second attempt. In like 3 steps, we were able to find the element we were looking for. Versus if I remember correctly, the array was like length of 13. So before that, we were taking like 13 steps to get to there, right? Okay, so less number of steps, like binary search, like 3 steps, versus the linear search, which took like 13 steps, right? So less number of steps means it's more efficient. Okay, that's how we measure efficiency, right? More steps, of course, is the opposite part. The more loop it is running, the more inefficient the algorithm is. All right, remember this part, and then we'll see what it is. Okay. Now, the next question would be like, what do you define as step? I said that it doesn't matter, the number of lines is not the criteria for a number of step. Okay, then what does number of step means? Number of step is an instruction that a computer is taking. Okay, that's how we define a number of step. Okay, these are the example that you see on the screen. These are all steps. When you're adding something, that's a step. Okay, computer is doing something. When you're assigning something, that's a step. When you're looping through, that's a step. All right, when you write the instruction between the for loop, that's one step. Now if your for loop is running continuously, what does it mean? It's taking those multiple steps. Each time your for loop runs, that's one instruction added onto it, right? So if my for loop is 10, running from 0 to 10, this means I'm taking 10 steps. Why? Because it's repeating. All right, that's how you determine it. Very important point, and you will see in the next one. Yeah. Okay. So on the screen, you will see 2 algorithms. Let's call it algorithms. All right. The 2 function, the first function has a for loop, and the second one is just returning something. All right. So the question is, what is the number of instruction for the second one? Let's start with the second one. How many instructions are there? Huh? How many? 1. You guys see it? There is literally just one instruction. What is that? It returns the first element of the array. That's it. Just one instruction. Okay? What about the first one now? Remember what I said about the for loop? How many instructions are there? 1 plus length. That's the correct answer. I don't know what the length is, but whatever this length is, that's the number of instructions. Right? Because it's going to start from 0 and it will go to the length -1, like whatever the length of the array is, and then it's going to console log these. All right? So this means the number of instructions in the first function depends on the length of the array. Yes?
So do you count just the console log list I, or do you have to count the comparison of I to list length and the incrementing of I as?
You can count that too. Yeah, we'll count the complete thing. But the comparison, yeah, you can count comparison also if you're trying to be really strict. But in the bigger scheme of things, that one instruction doesn't really make any difference. So the question is, do I count? Because you remember how the loop is going to end. It's a good question. That it's going to keep looping, and the last time it's going to compare, right? It's going to fail, and then it's going to come out, right? That's how you exit the loop, right? It's comparing this each time, and when the length exceeds, then it comes out of it, right? So that's one calculation, right? Again, the question was, do I count that as part of the instruction? Yes. But does it matter? The efficiency with just one instruction doesn't really matter in a big scheme of things, right? If I'm looping through million rows, right? I'm doing million instructions, right? Million and one won't affect anything. Okay, but yeah, you can count that as an instruction
Does the
also.
computer not do that comparison every single time?
It does every single time.
So wouldn't that really be 3 instructions every time it goes through the loop?
What are the
You
3
compare
instructions?
One to increment I and one to actually do the instruction.
One to increment. Yeah. But again, these are the number of instructions that you do over here are the same as over here, right? So like if it's doing 3 over here, it's going to do 3 over here. So in end result is 6, right? If you are doing million, it's doing 2 million. So the efficiency between million and 2 million, wouldn't make any big difference over here. It's going to be inefficient if it has to be, but it won't really change a lot of stuff. That's why when we come to it, when we measure the efficiency, we'll see we are approximating what's going on.
So it's still linear.
Yeah, it's still linear. It doesn't matter. Yeah, it's linear. Why? Because it's going through each one. Okay. All right. So now, if I wanted to ask that which algorithm is efficient, remember our definition of efficiency: fewer steps. So which one of these algorithm would you say is more efficient?
Second one.
The second one. Why? Because it's taking less number of steps. Right? Why? Because it just literally just one step. Okay, so in a big scheme of things, if I pass in 100, an array of 100 length over here, I'm going to have approximately 100 instructions, like 100 steps. Over here is going to be 1. If I pass in 200, it's going to be 200 or something. Over here, it's still 1. Okay, it doesn't matter what the size of the array is. The second algorithm always is faster. Okay, because it's fewer numbers. So now, does it serve the purpose what we are trying to achieve? It doesn't matter. That's not what we are concerned about, right? Those totally seems like they're doing 2 different things. The input is the same, that I'm getting an array. Within this function, it's doing something different. We are not concerned about what it is doing. What we are concerned is what are the number of steps that this one is taking and this one is taking. And just based on that, we are trying to determine if this is efficient or this is efficient. And you guys came to the right conclusion that this is more efficient. Okay? Why? Because it takes less number of steps, which is literally 1. Okay? Let's see. So we counted the instructions. We came to this, that the second function is actually just 1 instruction. The first one is taking n number of instructions. N is the length of the array. Okay, if there are 100 items, it's going to loop through 100 times. We concluded this. Let's get back. Okay, so time complexity. The first thing is how much time it is taking. So the more number of steps, the more time it takes, right? Does that make sense? The more the computer has to run the instruction, the more time it's going to take. So the second one is going to take less time versus the first one. Okay? It's a very simple example, but we'll get to the more complicated ones. Okay? Again, this is what I explained, that it doesn't matter what is the length of the array. The second function, the head one, is always going to be efficient because it's going to return just 1 instruction. It's always going to execute 1 instruction versus the first one. Okay? So the time efficiency is, it doesn't matter what the length of the array is. Your head function is always going to take the same amount of time, right? Okay, a constant time is always going to take the same amount of time no matter what you pass in, right? So that's like the definition of the most efficient algorithm, that no matter what you pass in, no matter what the number of array is, it always executes in same time, right? I don't know, extremely unachievable, but that's the definition of the best algorithm ever, that no matter you pass in 100, 1000, 2000, 1 million, the length of the array, the function always runs in the same time. Okay? Versus the other method, right? It kind of increases over time, right? The bigger the number of elements in the array, the more time it's going to take, right? So that's like considered like one of the most inefficient algorithms, right? Well, actually, that's not true. There's a little bit more. We'll see what that one is. But between these two, that's what it is. All right. The second thing, we talked about time. There's something about space also. So the complexity is based on time and space, right? Now, the time we already determined that the first one takes more time, right? But the console log, it's taking up some space. Do you guys see that? Why? Because in memory, it has to console that log, it has to store that variable somewhere in the memory and then kind of print it out on the screen, right? So some part of your memory is also being used, okay? The same with the first one, right? It's taking longer also, and it's taking more space also. Why? Because now I am console logging 100 elements. I'm taking that some space in memory. Okay, so the time also goes with space also. So you will see the word time space complexity. Both of them are kind of used together. Okay, now let's go back to the time. If you double the array, the time has doubled. Okay, we are talking about the first algorithm where we are looping through an array. If you triple the array 3 times, the time also goes up by 3 times. Okay, is this clear? Do you guys understand? Kind of, right? Keep going up. Now, what happens is you kind of keep generalizing this thing. Okay, we'll come back to this. Is kind of we are kind of gearing into what I talked about big O, and I was just remember the time complexity and the space, and then we'll kind of segue into that. Okay, so the time complexity, the definition is the rate at which the algorithm slows as the input grows, right? That's what it is. That we are trying to determine how much time, now how efficient this algorithm is, and what's the best way? See how slow it gets as the input grows bigger, right? If the algorithm is getting slower and slower as the input is going, this means that this is not an efficient algorithm. We cannot use this in cases where we have big arrays, okay, or large amount of data. We're kind of slowly getting into the data side, and that's where this algorithm comes in, okay? For example, the sorting one, if you're doing linear search for smaller arrays, okay, you might not see it because we have like faster computers today, but compare it with 1 million, 2 million, 3 million elements, right? As it grows, as the input grows, the algorithm is going to get slower and slower and slower, okay, versus binary search. All right, this is, I'm trying to get to the good part. All right, so what is big O notation? We talked about time and space complexity, right? The name for that is called big O. When they're talking about big O, this means that they're asking what is the time complexity of this algorithm, like how efficient that algorithm is. Big O is associated with efficiency of an algorithm, okay? So anytime somebody asks you, hey, you wrote this algorithm, it is running, for example, let's suppose we were looking at that question, right, on a couple of weeks ago, right? There were some for loops and while loops, right? Once you write that, code that out, the next question would be, hey, what's the big O of this algorithm that you wrote, okay? Or they'll ask you, what's the time complexity of this algorithm, right? Basically, they're asking, what is the big O, or how can you define that this much time this algorithm is going to take? Okay, basically they're asking that please tell me the algorithm that you wrote, how much time it's going to take for bigger input. Is it going to get slower and slower? If it is, then they will ask you, hey, is there an efficient way where you can write this algorithm? And remember, Nick came up with a better way. He kind of took completely the for loop out. So the complexity, so this algorithm was slower versus what he wrote became more faster because you took the loop out. All right. Now let's see what it means. Now remember the head example from the previous slide. It was always constant time, right? It always had one instruction. Okay? So the big O for that we call is 0, 1. That's not 0, it's O1. O1 basically means the 1 over here doesn't mean that it's running one instruction. Well, that's what it means, but it has nothing to do with that algorithm that we saw. You could write some other algorithm. Basically, O1 means constant. That no matter what input comes in, it's always going to be constant number of instructions. Okay? No matter how many input, no matter the array size is 10 or 100 or million, it's always going to run in constant time, right? So to denote constant time, the big O is O and 1. Okay? So now somebody asks, let's suppose you wrote some algorithm and it is actually running in constant time. You kind of determine that it doesn't matter what the size of the array is. The TV is not working. But it's always going to run in constant time. Okay? Every time you want to do constant time, you're going to say the big O for this is O1. Okay? You won't say O2, O3. Maybe there are 3 instructions every time. It doesn't matter. We always generalize this concept. All right? It comes to O1. Again, there might be 3 instructions now in head. If I create 2 more variables and assign something, let's suppose in my head I created 2 more variables and maybe just added these 2 variables. Okay. Okay, so these are like 3 instructions. So you wouldn't say now my algorithm, how many instructions there are? 3 now, right? I'm assigning 1, I'm assigning 1, I'm assigning 1 over here. So basically 3 instructions. So you won't say it's O3 now. Okay? Big O is all about generalization, right? You would say this is still run in constant time. Okay, it's always going to have 3 instructions no matter what the input is. Is that correct? Right? It's always going to be 3. It doesn't matter what you pass in, right? So big O for that would be 0, 3. But you wouldn't say 0, 3, you will still say, O1, like constant time, right? So always remember, every time you want to tell that your algorithm runs in constant time, the notation you will use is O1. Okay? Everybody clear on O1? That's probably the easiest one. All right, the second one, ON. Any idea what ON means? Looking at O1? Callback. Good try.
For any number?
Huh?
For any number?
For any number, but what number?
Size of the input.
Size of the input, right? Any number or the size of the input.
Mm-hmm.
Now, what this is saying is, if my array is 100, this is going to take 100 time. If my array size is 1000, it's going to take that much time. If it is 1 million, it's going to take O. Okay? O and that number. So basically, that kind of algorithm, we generalize and say it runs in ON time. Okay? And generally, ONs are if you have one for loop. Okay? Any algorithm that you write and you see it is using one for loop, right? You can kind of guess it's going to, and if somebody asks you how much time it's going to take, in big O you will say ON, right? Why? Because that's what's going on. So if I pass in 100, it's going to run 100 times. Okay? If I pass in 1000, it's going to run 1000 times. Okay? Again, generalization. Now you might have like a if condition over there. Okay? For example, the search algorithm the linear search, right? It has an if condition. And let's suppose we get lucky and the number that we are looking for is the first one. Okay? And you exit out. Now what happened now? How many instructions did it run? One. Now would I call it constant? No. Again, you generalize it. You got lucky, that's okay. Again, what was the, how do we measure this algorithm? Do we take the best case? What did I say on? Worst case, right? We always consider the worst case. So worst case means that my search thing is the last element. And if I'm taking the worst, it always will come to ON. Okay? ON means that the bigger your input, the more time it's going to take. It will grow by this much time. Okay? Again, what do you think? Is this efficient? Owen? Could be. Best you can get? Well, binary search is faster than this. It's actually faster than ON. ON, I'll show you a graph towards the end. ON is still considered inefficient because you cannot use an algorithm which is giving you ON and the reason is if you have 1 million rows, you cannot expect it to take this much time to run. Okay? Not only it will take more time, you might run out of memory and all that stuff. Okay, it's taking more space also. Remember, it's taking more space. Okay, so ON is also not a really efficient algorithm. And how we can say this, remember we did the linear search and we kind of came to the conclusion that it's not efficient. Then we did the binary search. Okay, and then we kind of said that, okay, this is more efficient than the linear search. All right, so ON is not as efficient, but it's still not as bad. I'll show you some really worse ones. Okay, this is still okay. All right, and once we see the worst ones, we're going to analyze. I'm going to put Matt on the spot. We're going to analyze Matt's algorithm that he wrote on that class. Remember 5 for loops? I'm gonna make him feel bad for that algorithm. All right. So what are some other ones? What about this one? How many loops do I have? 2. You guys see 2 loops? Okay. How much time does the first loop take? N. Okay. Everybody see it? N time. What about the second loop? Same? N. The second loop also takes n times. So what is the total running time of the 2 loops?
N
Squared. Does everybody see it? Right? N times the first, like the permutation thing. It's going to start from the 1, and it's going to run n times for that one. Then it's going to come back to the second one, it's going to run n times for this one. Then it's going to run third time. It's going to take. Basically, it's going to run n into n, which is n squared time. Okay? Now, what is the big O for this algorithm now? Considering what we saw?
ON squared.
ON squared. Okay? Now consider the input. If the input grows, how much time it is taking? It's taking square time.
Exponential.
Right? Now consider the 5 loops that Matt wrote. How much time does that take?
Wow.
N to the power of 5. Yes, exactly. And that's the response I'm looking for. Okay? Right? So for just, if there were like 10, if it's n to the power of 5, and then you had an array of just 10 elements. Imagine how much time it's going. It's going to take 10 to the power of 5 instructions to complete that loop. In the worst case, we always consider the worst case. Okay? All right? Again, if you're writing an algorithm, you're whiteboarding, I will tell you that 2 loops is too much already. All right, the solution with 2 loops is the one that people are like, okay, you are new to programming, or you are doing it. This is the first kind of algorithm that you come up with. Okay, and then the second question is always going to be, hey, this is inefficient, right? So how do you improve that? Okay, but as you go more senior, as you go practice more, you will think about this solution in your mind, but you will talk it out and you will tell your interviewer that, hey, this is what I'm thinking. Create two for loops, and I can come to this conclusion, but it's not efficient. And they will, that's what I do now with more experience, and they're like, yeah, at your level, you shouldn't even be typing this solution. Right? Yeah, so I already I talk to them and say, hey, in case that I never come to a solution, they will at least give me some point for my 2 for loops, right? It's kind of easier to see. Okay, for you guys, again, start with the 2 loops, the 2 for loops thing, but always remember this is always going to be inefficient. There's always going to be a better solution than using 2 loops. By this definition, more than 2, I'm not even going to talk about. Okay, there's no solution with more than 2. Okay, there is a better way.
Heard it here first.
Yeah. Okay. Now, so you see the problem. The more loops you have, the power kind of goes up. Okay. Again, now the same thing I've already said that you guys know it, but I'm just going to repeat it. The if condition over here doesn't matter, right? Again, the best case, this would only run one time, but we don't consider that. All our algorithms are based on the worst case. Okay, always remember that. So, you don't start arguing with your interviewer that, hey, I do have if condition. What if it's the first one I'm going to get out over here pretty quickly, right? It doesn't matter. It's always going to be n squared. Again, it's a more approximation, more generalization. Remember the for loops one. One for loop, n, two for loops, n squared, three for loops, n to the power 3, n cube, and then just keep going. All right? So if you think n was inefficient, remember n squared, n cube, and n whatever the times is getting worse and worse and worse and worse. Okay? And it gets worse really, really fast. You guys see that? Like by the third, n cube is like staying 3 times more. 4, 5, 6. It gets inefficient really, really, really fast. All right. Let's see. All right. You must have heard the quadratic keyword. Nick talks about every time. He was mentioning this. He was saying quadratic big O or quadratic time. This is actually means n squared. All right. This is just a different term. All right. So I already talked about it. 2 nested for loops keeps going. Again, I don't want you guys to get confused. So I'm going to clarify this. The key is nested loops for I 1 to n, and then for j 1 to let's go with n. Okay. Nested loop means the power, all right? This is different from for 1 to n, and then for 1 to n. Let's say this is I, this is j. These are not nested. You guys see it? These are not nested loops. What is the big O for this one? Huh?
What, the second one? N plus n?
Yeah, 2 n's, right? 2n, and then in big cases, the 2 doesn't really matter. So you can come to the conclusion saying it's extremely general. Okay? So you see, nested one is the power one, but if they are not nested, it kind of comes down to 2n or n approximate. Sometimes let's say this n. Okay? Everybody get that point? What I was saying? So the worst ones I'm saying is the nested ones. All right. We'll come to binary search towards the end. Okay. Let me see. Okay, this is the one I wanted to go through. Let me go back. All right. This is the binary search tree, and there's a data structure, so I'll come back to it, and I want to explain how this is constructed, right? Most of you or some of you already might know that how this is done, but I will come back to this, how do you create. But the one that we have seen is this one, binary search, all right? We saw linear search, and we saw binary search, right? If you're trying to do something, what do? We have this, and then half further, and then half further, right? Until you find the element, okay? So if you're trying to find for number 3, okay, it's going to take 3 steps, right? Why? The first, then half, then it's going to become half, and then half more until it finds the number 3. So it's taking like 3 steps to come to it, okay? Versus, let's find something that is, all right. All right. Does everybody understand that how the binary search is working? All right. It starts with the complete array, then halves it, right? If the number that you're trying to find is on the left, if it is less, then it will look over here. If it is more, then it looks over here, right? Number 3 is over here, so it's going to look in this half, then it's going to do another half. This time, if 2 is the midpoint, it's going to look for 3 on this side until it actually finds it or doesn't find it. Okay? All right. Now, the next slide basically says is this has 11 elements, right? If you add 10 more to it and you're trying to find still number 3, okay? How many steps will that take? So this time the array stops at 10. Let's suppose you add 10 more. 4. Okay? Again, just imagine, I mean, you can still be like 4 or 5, don't have to be the exact. Basically, you understand that if you grow the array, half, then half, then half, it basically takes just one more step. Okay? Again, what did we do? We doubled the array. Remember in our linear search, if you double the array, the time kind of keeps going up. Over here, even if we double the array, it was just like one step more. Okay? All right, do you guys see that this is much faster? Well, like really faster than linear search. Okay, even with doubling the array, the amount of time was still, maybe like one step more. Okay, now, basically what it comes down to is if you keep doubling the array, all right, square or maybe cube it or keep going up, the time keeps kind of like doubles, right? But still it's better because this size is increasing by a lot versus this time, right? So if I have an array of 10, this becomes 100, all right? But the running time is 20, all right? Now, if my array size is 10, this becomes 1000, all right? Let's suppose I have an array of 1000, right? But still the running time is 30. Okay, that's the running time for binary search. Again, you don't have to understand the mathematics and all that stuff. I'll show you a graph. But basically, binary search or something similar to binary search is kind of considered log n. Okay. Again, we saw a constant which is big O of 1. Then we saw one for loop big O of n. Then we saw n to the power x, depending on how many loops you have. Binary search is considered log n. All right. Let's see what log n actually means. Okay. If you're trying to find log of 8, okay, basically you're trying to find how many times you can divide that number by 2. All right, that's the log. Again, I won't go into much detail, but basically log of anything means that how many times will it take for you to divide the number by 2. So for example, if you're doing log 8, you have to divide 8 by 2 like 3 times, right? Because the first time you divide is 4, then you divide again until you reach the number 1. That's the basis of log. Okay? Again, you don't have to really understand it. The only thing you need to remember is that every time you are using binary search, the running time is going to be log n. Okay? And log n is definitely better than, well, not better than better than constant. It's kind of more like an unachievable one because there's literally just one instruction, but it's better than n or n squared. Okay? And this is for large number of arrays. All right? Always consider that when we are talking about these things, we are considering like large number of arrays. All right? It could be, maybe large could be 10,000, million, it doesn't matter, but it's like for large arrays. All right? So binary search is really good for large number of arrays. This might be good for small number of arrays, okay? But binary search is still better when we are using large arrays. All right, this is the graph that I was talking about. So first one is the easy one, the constant one, right? You see on y-axis you have your time, and over here is space. That how many? What do I mean what do they mean when they say data input or space? Memory. What about when we talk about arrays? Size of the array. All right. So this is basically the letter n. Okay. So you can see as the size of the array grows, it's going bigger, and the more time is this is taking. Okay. So the higher that you go on your y-axis, this means the more time it will take. The higher you go, well, the more right you go on your x-axis, this means your input or your n is getting bigger and bigger and bigger. Okay, do you understand the axis? Very important. Time and n. All right. So the first one that we saw, the constant one, it doesn't matter, right? It's always going to be, no matter what the size is, it's always going to be in constant time, right? And we had to come up with some number, and that's why you see 1 over here. Again, if you put log big O of 2, it's going to be, the line would be over here. Big O log of 3, it's going to be, it doesn't really matter, okay? Again, these are more general, so that's why big O of 1 has been chosen. And any algorithm that has constant time, we call that big O of 1. All right, let's look at the second one, big O of n. Okay, you guys see why it is exactly vertical, exactly like cross, right? The more the number of input, the time goes up. Okay, over here, this much time. Okay, over here, this much time. So the time kind of grows as the size of the data structure or array kind of grows. Okay, and it's extremely straight. Okay, now anything that is below this is more efficient. All right, depending where it crosses. We'll take a look at that one. Okay, let's look at the squared ones. So the squared one kind of starts off, you see, for a small amount of data, it's still okay. Less time, less time, less time. And then suddenly kind of shoots up over here. Where's squared? This one. Okay? So you see, for a small number of increases, the time is kind of going up really, really, really fast. So we call that exponential growth. All right? After some point, this is going to become almost straight. So no matter what, how large your input is, it's going to be inefficient. It's not going to work any better. Okay? So you see how it is going? So this kind of a curve, if you remember, is called kind of exponential growth. Now look how the n cube is. It's even worse. That okay, n squared is taking a little bit more time to kind of taking more input to kind of go bad, but this one is like just over here and kind of shoots up, right? For this amount of data is going to take this much time, right? Similarly, kind of keep increasing the power. Eventually, you will come that it's going to be like a straight line. No matter what your input is, it's going to be extremely, extremely inefficient. Right? So that's why we say that these ones, the quadratic ones, they have exponential growth. So you have to be extremely careful with those. Right? The more for loops you have, you see the small amount of data is going to take a lot more time. Okay? I would definitely keep this graph as a picture. Kind of helps me to visualize every time I'm like, studying for an algorithm, or somebody asks me what's big O going to be like. So I know which ones are more inefficient, all right, which ones are more efficient. So I'm trying to achieve something that is more reasonable over here. So log n is binary search. So you can see it kind of starts off slow because for smaller inputs, it's kind of considered inefficient. But for larger inputs, the time isn't going up by much, right? That's why it's called that for larger inputs, binary search is really, really good. All right. Now, among these algorithms, you're kind of trying to strive for something that is log n. All right. This, I don't know if there's an algorithm that is constant times, kind of, that no matter what you give in, it's going to return you. But this is more kind of achievable. Okay. All right. Let me know any questions you guys have. Kind of getting the idea what it is. Again, it's more about the concept. Okay, nobody's going to ask you that how do you came to this or how did you come to this. The question would be, okay, every time you write an algorithm, what's the big O of that algorithm? Usually, it's going to be one of these, right? It's probably not going to be this. Well, there are some data structures. We'll take a look at it. But when you're writing an algorithm, usually it's somewhere over here, okay, as a first go, and then we try to come to a conclusion where it's more efficient. Yes.
Does log always mean log base 2 event, or just something that's in
No, it's log base 2. Yeah, that's what you're doing. Okay. Again, keep this in mind or keep this handy. If you don't remember this and you're trying to find like what my algorithm, like what's the big of your algorithm, kind of try to understand that, oh, if my array size keeps going bigger and bigger and bigger, which graph depicts more for my algorithm? Then you can come to the conclusion, oh, is it this one, is it this one, is it this one, or is it this one? Right? That's kind of helps me that when I'm trying to come and I'm trying to visualize that what's the big of my algorithm. This kind of helps me. Well, I think that, oh, if the size grows bigger and bigger, is it more towards this, or is it like kind of going up, shooting up? Right? If it is shooting up, then I know it's n power something. Right? If it is not, if it's kind of slowing down, then it's probably somewhere here or here. Okay. All right. Any questions? All right. So data structure. What is data structure? Okay. Now before you answer, try to break that word down. Data and structure. Okay. When we talk about data, remember what I was saying about space, right? Every time you use something, use an instruction, you are basically using some part of the memory. Okay. So that part of memory is saving your data, right? When I create a variable, what is going on? I'm creating some variable on memory and I'm saving some data, right? 0 is some data, right? I'm saving this into my variable. Okay. So I'm using memory. Okay. So every time we talk about data structures, always remember that we are talking about the computer's memory, that how our data is being stored in the memory, right? Basically, how our data is structured in the memory. This means data structures, right? That's where the name comes from, right? How our data is structured in computer's memory, right? So in this few slides, we are going to look at some different ways. Again, as soon as I start showing you some of the different ways, you will say, oh yeah, I know this, all right? Let's see. Again, this is not as important. All right, first data structure. You guys remember this one? Arrays. Arrays are data structure. Why? Because you are storing some data in this structure, right? And this is being stored in some way in your memory. All right. So the arrays is the basic one, the first one, probably the easiest ones also. All right. So when we talk about data structures, array is one of them. All right. And how does the array stores the elements? In an order, right? In a sequential order. Start with index number 0, then 1, then goes up to some number. Okay. Now, arrays in JavaScript are, as JavaScript is weird, it's kind of different, right? You can store mix things in JavaScript array. In any other language, this is not possible. Seriously, you can have a string, you can have a number, you can have double, you can have float, you can have an object in JavaScript in array. JavaScript will never complain, but you can never do the same thing in any other language. In any other language, if you declare your array as a number, it can only take a number. It cannot take a string. All right. But since we're concerned with JavaScript, basically an array is you store some data in your array, right? And they're more sequential, right? 0, 1, 2, 3, 4, and you kind of keep adding those. Okay. So array is the first one. Okay. We saw some of the methods. How do you add elements to an array? Use a push method. Everybody remember the push method, right? Array.push, and it will. Where does it add the element? Start or end? At the end. Important point to note. All right. Remember that. So when you use push, you add an element to the end of the array. Okay. Now JavaScript. Another thing that is different. In other languages, when you're declaring an array, just an array, there are different data structures in other languages. When you talk about an array, you have to give a size when you declare the array in any other language, right? You have to say this array is going to be 10, right? It's going to have a length of 10. This means it's going to have elements from 0 to 9, okay? In JavaScript, you don't have to mention that number, right? You can just keep pushing and it kind of increases the size of the array. Yes.
So in another language, if you want to push, you just have to make a new array.
There's no push in other language.
What's what I'm saying? You have to make a
Oh
new
yeah,
array
you have to make a
and
new array.
build
Yes,
it.
yes. They have different data structure. The other one is called array list. Again, it's specific to different. C# has it, Java has it. It's kind of mix of a list and array, and that has a push method or add method, which kind of adds to that. But array, like this one, like square brackets, you have to declare. You have to say what size the array is going to be as soon as you declare it. In JavaScript, it doesn't matter. This array is, I don't know, infinite size. You can just keep adding until you run out of memory, and JavaScript will never complain. All right. Now, the second question: what if you have to add at the beginning of an array in JavaScript? Anybody knows? There's a function, and I have never talked about it. I don't know if anybody used it. If you want to add, so push adds to the end. There's another method that adds at the beginning. What is it? Yeah, we'll come to that. That how do you add it? But that the thing. This question is. I'll come to this question. But there's a method that you can add in JavaScript. What is it? Prepend. That's kind of close.
It's something like that. I remember looking at
I'm not sure. Anybody see it? It's called unshift.
I remember reading it, just being like, "What?"
Okay. Now, okay. So the method is called unshift. If you want to add a number at the beginning of an array, you use the method unshift. All right. Now let's go back to this question that Matt was saying. Matt, how would you add? If you had to do add an array, add an element at the beginning, what would you do?
And something at the end.
Then shift everything, right? That's why it's called unshift. It basically shifts all the elements next, adds one more shift, and then just adds one over here. Okay? So what am I doing? I'm basically looping through. I'm saying, oh, loop, run a loop, take one element, kind of shift them 4 plus 1, 3 plus 1, 2 plus 1, 1 plus 1, 0 plus 1. Oh, this is empty now. Now I can put my element over there. So basically, unshift method, if you can believe, is actually literally doing this thing. It's not very efficient, but that's what it does. It kind of shifts your elements by 1 and then adds the number that you want to the first of your array. Kind of similar one.
Is it literally doing that, or is it shifting the indexes?
It's shifting the indexes around and then kind of do it. Okay. You guys actually see this and understand what's going on? That's a big win if you can actually see and understand it. Right? It's looping through the array, and what is it doing? It's taking the next one, kind of assigning it, and then in the end, everything has been shifted. The index number 0 is empty, and it adds whatever number you want to shift. Okay? So if you want to add an element at the end of the array, it's push. If you want to add at the beginning, it's called unshift. Right? Unshift will do this for you. Okay? All right. And then you guys see the inefficiency, right? That it has to shift. So the bigger the array, the more shifting it is doing, right? It kind of increases. So the big O for this case would be n, right? The bigger the array, the more shifting it has to do. It has to do one shifting less, but again, we are approximating, so it kind of comes down to n. Okay. All right. Any questions about array? Everybody good? All right. These next two are new. I don't know if you guys have heard about it. Stacks and queues. Anybody know what stack is? And queues?
Stack is like.
All right. It took me a few seconds to. I was like, what overflow? What is he talking about?
It's the stack where you're trying to do certain things, and it's like you build a stack and it's waiting on certain things to come back, and then it like collapses.
I see what you're saying, but that's a really advanced definition actually. Stack simple stack. What's a stack?
Stack is last in, first out.
Right. Again, simply, you both are right, but stack is you're like stacking on top, right? You stack boxes, right? You stack stuff, right? That is literally what this data structure is. Now when you're stacking stuff up, okay, let's keep this one, okay? What Matt was saying. Now if I want to pick the box from my stack, I'm going to pick the first one out, okay? So this was the first one that came in, right? But this is going to be, now if I want to remove these, right, I want to unstack them. I'm going to take the first one first, then the second one, then this one, then the last one, okay? So the first one that came in is the last one that goes out. You guys see that? In a stack, you are putting things on top. You're stacking them up, right? The first thing that came would be the last one to be taken up, right? Why? Because this has to go to this, then it comes to this, right? So the first one in is actually the last one out. Okay? Philo, philo, whatever, I call it philo, but whatever makes sense to you guys. Remember, stack is philo. First in, okay, last out. That's what it means. The first thing that comes in will be the last one that is out. Okay? Now, let's see. Yeah, it's called Tower of Hanoi. I don't know. There's a whole problem around it. Okay. What about when you do the push to an array? You see, it's stacked. It's just side stacked, but it's still stacked. Like you are going to add a new one at the end of the array. Okay. So that kind of considered the push, kind of considered as stack. But let's not go there. But that's what stack means. Now, JavaScript doesn't have like a built-in data structure called stack. You can simulate it, and I'll show you some code how do you do it. But basically, this is the logic that the first element that comes in will be the last one that is out. All right, that's what stack means. Now, other languages have defined data structures. They actually have stacks and queues. JavaScript doesn't have it. Right? So similar logic. What about queue? Now, what do you think queue is? What is it? FIFO. Oh, okay. Yeah. First in, first out. Queue is basically when you form a line, right? You're trying to get into some show. The first one who gets there first is the first one who will go in. Okay? So by that, it's called first one in is the first one out. Okay? So queues are FIFO or FIFO. Alright? And stacks are FIDO or FIDO. Alright? Remember that. So again, queues, similar to stacks, JavaScript doesn't have a data structure called queues, but we can simulate this. Alright? Now, we saw two methods for array.push and unshift. Alright? Do you guys see what would be a stack and what would be a queue? Push would be a stack and unshift would be a queue because you're putting the first one over there. We'll come to that and we'll see how do we structure it. But that's the definition of a stack and queues. Let's see. Send first out. These are the slides that I just talked about. You keep the element that comes in kind of goes on the top. Okay. So when we are talking about stacks, remember the stacks. This is the one, and then if you want to add another one, it adds to the top, then top, then top, then top. Okay. Before we get into the coding part, any questions? Do you guys understand what a stack and queue is? All right. Again, very popular data structure. Every language usually has it. JavaScript doesn't have it, but you can still create this using array.push and array.unshift, and we'll take a look at that. But stacks and queues is an extremely popular data structure also. All right. So arrays, stacks, queues. Now, take a look at this. What are we trying to do? So you see there are three methods over here: push, pop, and peek. Okay, so push is similar to our array.push. Okay, what are we trying to do? We're trying to create a stack kind of emulate stack data structure in JavaScript. All right. When we are trying to add something, it should be at the top of the stack or at the end of the array. If you have shifted like this, it's always to the end of the array, right? And for the end of the array, the method is push, right? So you see, if you look at the push method over here, what does it do? It just takes the item, the element, the one that you're trying to insert. It uses the array.push, right? Simply why? Because this will add it towards the end, and a stack is basically it adds the new one on the top, right? And then if you just flip it 90 degrees, basically this is the end of the array is your top. Okay, you guys see it? All right. Now, what about the pop? Now, these keywords, pop and push, these are popular ones, and in any other language, you will see that when you talk about the stacks and when you're using the data structure as stack, the methods are called push and pop. Okay, so popular ones. So that's why they're using the same method name over here. Okay. Now, there is a pop method in arrays also. All right, what does pop do? Just by looking at it, grabs the last one. All right, if you do a pop, it basically goes to the end of the array and returns you the last one that was inserted. Okay, this is basically you're saying array then minus one. Right? What would array length minus one give you? The last element. Right? So array.pop does the same thing. It will give you back the last one. Now peek is interesting. What do you think peek is doing? Any idea what peek is doing? It is literally peeking. Yeah, it gives you, what is it doing? It gives you the last element. But it doesn't, what is the difference between pop and peek? So what pop does is, if you're using the pop, it will take this element, return, give it to you, and then disappear. This one is gone. When you do a array.length or something, this element is gone. It will literally pop it. It will take that element, return you the value, and then you can say kind of release it. That's what pop is doing. Right. Why would you want to do it?
That's the only way to step that up.
Right. That's the only way to kind of take it out and then reduce your array. So there are some algorithms that you want this array to kind of end also. You have inserted something, but now you want to make sure that this array kind of gets empty. For example, let's suppose we did the restaurant app, the hot restaurant or something, right? There's a waiting list. What do you want to do? When the person is served, you want this array to be reduced, right? That doesn't make sense, right? So that's why you would want that. Okay, so pop, again, pop will pop that element and that the array size kind of gets reduced, that element is gone, yes.
So is there a pop function built into arrays in JavaScript?
Yes.
That removes it?
Yes.
Okay.
Yes, that's what it is, right? And peek, what does peek do? Peek really peeks it, right? It's taking a peek at the last one, but it's not going to remove it. It's going to tell you what the number or what the data is on this one, but it will not remove it. Okay, that's why you see this way. What is this doing? This is literally just getting the last one and telling you, oh, this is the data, but it didn't delete or it does not reduce the size of the array. Okay, now, as I said, in JavaScript, these method does not exist. The push, there's no stack data structure in JavaScript, right? That's why, but in other languages, they are literally called push, pop, and peek, and but the function is still the same, right? Push will add towards the end or the top of the stack. Pop will take it out, remove it, give you the value back, and then it's going to reduce that size of the stack. Peek will always give you whatever data you're looking for at the top of the stack, but will not remove it from the stack. Okay, so it's building the stack. Pop is reducing the stack by giving you the first one. Peek will just tell you what data is on the top of the stack, but will not remove it. Okay.
What do pop and peek do with the arrays in?
You can add a check over it. It will just return what, -1. It will just give you an empty or throw an error.
Turn null?
Return, sorry, undefined or no.
So the peak is custom.
Peak is what?
The peak you have to write yourself. And pop is like
Right. These two are over here, but if we're kind of wrapping this around, yeah. Why? Again, the reason is because these already exist. Yeah, JavaScript doesn't have that stack, but in any other language, these methods will be there for you to actually use them. Okay. Now, similar concept, queues. What would I already went to the queue? Okay, take a moment and see how queue is defined. Same thing. JavaScript doesn't have queues also, right? So we have to make use of some of the array methods, right? Which ones are we using? Enqueue means you're adding it to the queue, right? So basically, if this is my queue, right? This is my queue, let's suppose. Where am I going to add the next element?
at the end.
At the end? Let's start.
If you're adding the element and you queue it up,
So this is my
you're not removing it.
queue. No, forget about the coding part. If I want to add something to my queue, where would I add it? The front. It doesn't matter. Forget about it. Forget about the coding part. But it has to be added over here. That's the point of the queue. Okay?
You can't cut in line.
Yeah.
But that's
First in, first out.
jump key. First in, first out. Huh?
Jump in the queue up in here.
What is it?
Number one is first.
Yeah. But I'm saying if you want to add something to the queue again from the data structure point of view, right? This becomes your 0, 1, 2, 3, 4, 5. If you want to add the one that you are saying, if you want to add in a stack, then you have to add it over here. But if you want to add in a queue, it's always going to be added in front of the array. And this becomes 0, 1, 2, 3, 4, 5, 6. That's the difference between stack and queue. Okay? Now, again, stack, if you want to add, it adds it at the end of the array. Queue will add it at the beginning of the array. Now, the pop one. If you are doing a pop or you take some element out from the stack, it's always going to be this one, right? What about queue? If you dequeue it, which one will come out first? Yeah, the first one. Okay, first one. This is the one that's going to come out. All right. Now, what are the?
So if this one's coming out, shouldn't we be adding it to the back?
No. Again, this is the queue. Again,
Right.
no. This one in a queue. Again, queue is kind of different. It's opposite of stack. All right. So stack you're adding towards the end. In the queue, you're going to always add in the front.
But then where are you pulling from when you?
You're pulling from the front. First in, first out.
Just like if you add to the front and then pull from the front, you're doing last call or steps.
What are we doing?
If you're pulling from the front, shouldn't you be adding to the
No.
back?
That's what I'm saying. It's
Is that
different.
referring to the array, like the item in the array itself? So it's like first into the array, like, and then it doesn't mean like this is becoming the first of the array. It just
Right.
means you place it to become the first in the array, and then you take the first of the array out.
Right. It's again, and I understand that the first person who comes in the queue will be here. The next one will be here. The next one will be here. The next one will be here. Now come to take this concept and come to the coding part. Right. Stack was if I add something, it has to be top of the stack, right? And then it kind of has you 90 degrees. This is the end of the stack, right? But the queue is that the element is going to be added over here. If I add it over here, then that's just the stack.
But aren't you pulling from the front?
Right. You are adding also, you're pulling also. That's what I was saying. Where are you pulling from? What is the shift doing?
But if you're pulling from the front, you need to be adding to the back of the line.
What is it? No, again, okay, let's see what is shift
Ditch the
doing.
queue analogy.
Right.
Ditch
It's
that.
No, actually that analogy is right.
right, but what is shift doing? What is shift doing? Oh, I see. This you're talking about this thing, right? It's actually adding towards the end of the. Okay, I see what. All right, he's right. So, where's the eraser? All right. So, if the new element comes in, he's right. It adds it towards the end, but when you're pulling it out, it just pulls from the first, right? All right. Let me do this. All right. So in a stack, 0, 1, 2, 3. In a stack, if I add an element, where does it go? Over here. Okay. If I pop an element, which element comes out? The fourth one. Right? Right. In the queue, Matt is saying is correct. I got confused. If I add an element, where does it go? It will still go over here. Okay? But when you pop it or when you take it out, which one comes first? This one. Okay? That's why you see, if you now look at the code over here, the NQ, you're adding it, the Q is the same as the stack one. It's pushing. So push always adds to the end of the array. Right? But when you are taking it out, shift is picking the first one and then returning it. Okay? Now, what's the difference? Again, I will come to the first one. Now, do you guys understand the NQ and the DQ? All right? Now, does it make sense? Well, I know, I understand what you were saying. I got confused with the shift one. Okay?
DQ, NQ.
So, last and first out. All right? Now, what's the difference between DQ and first? Think about the stack that we saw, pop and peak. What's the DQ and first doing? What's the difference between DQ and first?
DQ is pulling the first out and shifting the line, whereas first is just telling you it was first.
Right. Now, compare it to the stack one. Which one is the pop and which one is the peak? Like, compare.
First is the peak. Yeah, first is the peak.
First is the peak. You guys see it now? Right? You are peaking it, yeah. It tells you what the first element is, but it doesn't, like, kind of delete it or remove it from it, right? DQ actually takes it out and shifts it and, returns it and kind of removes it. So this one becomes 1, 2, and 3. Okay? Again, push, pop, and peak in stack. When it comes to Q, it's called NQ, DQ first, right? Same thing. NQ is same as push. DQ is same as pop. First is same as peak. Alright? It is important to remember these names because these are the names that other languages use. Alright? The languages of Java and C#, which have stacks and queues that define data structure just like an array, they use these keywords. Okay? Again, in JavaScript, these don't exist, so that's why we kind of have to make it through. Let's see what is. All right, any questions? Stacks, queues, arrays?
So are queues like a little bit inefficient in JavaScript because they're not built in natively and you have to like shift the whole array?
Yeah. Okay. Linked list. All right. Oh my God, these are the worst ones. And these, I hate every time somebody asks me this question. Hey, can you reverse a linked list? Can you? Oh my God. Anyway. All right. So linked list is kind of an array, but look at the name, link and list. All right. So it is a list which is being linked. And how are these linked?
Pointers.
By pointers. Excellent. You should be glad you guys are not studying C++ or C
or C. I already tried learning C.
This
is exactly where I stopped.
Yeah.
I was like, wait, you're pointing me somewhere?
I didn't have a choice to stop. I had to actually study it to pass it. All right. So linked list means that you create a list and it has information about the next element. We'll call this element, and then we'll come to the right name. Okay. Now, what do you see over here? Linked list actually knows, it creates a link and it knows what the next element is. And when we talk about linked list, this element is called node. Each one of these are called nodes. Okay. So each node, the first one is usually called head node. Okay, this is your starting point of your linked list. Okay, after that, Everything else is a node, and the node has two things. Each node has two things in it. The first thing is the data or item. It doesn't matter what it is. Basically, the data that it is holding. It could be a number, string. It doesn't matter. Okay. The second part is the link to the next node. Okay. Again, over here, item, data, and then the link to the next node. Okay. Item, data, link to the next node. Now, if this is the last node, the next link would be null. Right? That's how you do it. Okay. If you reach a null, if there's a the next of some node is a null, this means you have reached the end of the linked list. Okay. But from the concept wise, this is what a linked list is. It is a list which is kind of linked, and you see it's linking by some information, and that information is it knows which one is its next node. It doesn't know which one is this node. It doesn't know which one is this node. It only knows the node that is next to it. Okay. In a simple linked list, that's what it is. It only has two information: one, the data or the item, right, and then the link to the next node. In it also has another name. It's called single linked list or singly linked list. Yes.
What's the benefit of this sort of data type?
All right. So the benefit is if you're trying to shift. Remember what we were doing? You were trying to in the previous one, this shift method, right? It was running that loop and kind of shifting towards it, right? Linked list kind of comes in. You don't have to write a for loop for it. What you're trying to do is you're trying to find the node and then kind of shifting everything. You're basically what you're doing is you would do is if I let's go back over it. In this array, right? If I want to shift, what do I have to do? I have to run a loop and I have to say, oh, add this one, move here, then move here, then move here. How many instructions? N number of instructions, right? If I want to, what am I trying? I'm just trying to add a number at the beginning of the array, right? Now in linked list, if I want to do the same thing, what would I do? I would create a node, new node, point the head to that node, and point the new node next to this one, and done. Right? What? 2 instructions. You see how more efficient is it versus going through, oh, shift this, shift this, shift this, shift this, shift this, versus just point, create a new node, new constructor, create a new node, point your head to that one, and the next of the new node would be this one. That's it, and done.
But if you're looking for something, you just gotta sit there iterating through the whole thing.
Yeah, if you're looking through it, yes, you have to iterate through. Well, you have to do in linear search. You have to do the same thing. Right? We can use binary search in there. Okay. So linked list is definitely the next step. Instead of using arrays, you will see linked list is used for more efficiency. And one of the examples that I just gave you, right? That when you're shifting, it's kind of much easier over here. If you're trying to insert something, it's a little bit easier. Find the item and kind of insert it. Okay. Again, same as stacks and queues. There's no data structure as linked list in JavaScript. And I can see it, right? JavaScript was meant to be quick and dirty and easy and get your website running, so they don't have these complicated data structures. But again, with Node.js and people, they want to attract more programmers or backend developers, right? So these are more natural to people who are working in backend. Linked lists, they're more familiarized with linked list stacks and queues and all this stuff. So these kind of concepts are coming through it. Right now they still don't have any built-in functionality, but still you can create them. Okay. So the creation is I don't have to go through this one, but just understand that this is a node, right? So it could be a JavaScript class or like a class node which has 2 things: item or data and the next pointer. Okay. Next is basically another node, and then you are basically telling when you're creating an array, you're saying, oh, this is my next node, this is my next node, this is my next node. Okay. Again, from the coding perspective, you don't have to remember the code. The only important part is you understand what a linked list is and how they are linked together. Okay. Again, 2 parts: the data or the item and the link to the next node. That's important. These are also called singly, literally it's called singly linked list, right? There's another one called doubly linked list. Doubly linked list has three information: data, next node, and it also has previous node. That's the only difference. It's called doubly linked list. It can go forward and it can also go backward. It knows what's the parent of that node. Okay, so those are doubly linked lists. Those are even more complicated because now you have to have two links. Okay. All right. Any questions so far? Kind of getting the idea. We started with arrays, stacks, queues, and then linked list. I think there's two more. What time is it? You guys want to take a break and then look at the next 2 or 3? I think it's not that much. There's no more code anymore, but you guys tell me. You want to take a break? Is power through? All right. Maybe like 10 minutes more, I think. Okay. Dictionaries or maps. All right. These are one of the most efficient data structures in any language you will find. Okay. And what these are kind of similar to your object thing. All right. But these maps have two things in it: key and value. We call them key value pair. That's what map is. Now, if you look at the code over here, this is the key and this is the value. Key and value, key and value. Okay. These kind of save you from creating a for loop and trying to find something. You can put your data in a map, and then you can just use the methods exactly trying to find that. Let's suppose I'm trying to find the word pigeon over here, right? How many instructions will it take to find that pigeon? So this is my map, okay? And I want to find the key pigeon from it. How many instructions will it take me to find that pigeon? How many? Just one, right? Map.get, and it will get me the right one. Right? This is one of the data structure which is 0, 1. Like it's always going to execute one instruction. It will get you back what you're looking for. Versus if you had this as an array, you have to loop through and try to compare each one and try to see if it's a pigeon or not. Maps are, what they do is they keep like a key value pair, and they can actually go ahead and find instructions just like one instruction. And for example, the method over here is called get. So you can just say, hey, map.get, and give the value, and it will give you what you're looking for in just one instructions. Okay? No. No. In the backend, it's a little bit more complicated. They create like some hash codes, and they are kind of indexing like data sets and like databases. They are keeping some kind of index, and they kind of hashing it through, and that's how they find it. Okay. So that's what map is. All right. Again, if you come across in JavaScript, these are called maps. In other languages, you will hear the word hash maps. You'll also hear hash tables. There's another one called set, but they kind of are on the same data structures. Okay, but for JavaScript, there's only one. It's called map, and what it does is, again, this is how you do it. With a new keyword, you declare a new map, and that's will give you a map. And what you do is, if you want to insert something, you use the keyword, you use the function set, and in set it expects two parameters: key value, key value, key value. Okay. And then if you want to get a value for a key, you use a method called get. Map.get, and then it will give you the key for that one. I'm not sure if there's a method. I know in Java there is. Not sure if there's a method where you can put in the value and it gives you the key. Usually that's not the case, but I've run into some issues where I wanted to give the value and I wanted to get the key back. Right? Again, that's what I'm telling you is from like an interview experience. But the solution for that was, well, if you want that, why don't you flip it and make the key, like flip the key and the value. That was the solution. But you can still get value. You can give the value and get the key back. I'm not sure if there's another method in JavaScript. But I'll have to look. I don't think there is that you can give the value and gives you the key back. Okay. Map.keys. If you had to take a guess, what is map.keys returning? Right. It's a list or an array. All right. Same with map.values. What about map.get? Just one object, right? So this tells you that this has to be unique. The keys are unique. Okay. Map has unique keys. All right. The last line is important. They're included in ES6. So this tells you that JavaScript never had. As I said, JavaScript wasn't built for data structures, but again, as Node.js, as more people are coming towards it, they have started kind of introducing these new concepts over there. So ES6 has map. It's not present before that. Oh, this is a good one. Trees. What is a tree?
Yeah. What is it's a resource we're running out of on this earth.
Yeah. So any trees is a general data structure for something that kind of draws out like this. Right? Any data structure that is kind of laid out in this format, you call it tree. Now, have you guys seen any data structure? It is kind of laid out like this. With trees. Oh, that is really good. Yeah, I thought I'll have to give more hints. Yeah, DOM, excellent. Remember the DOM? DOM is actually laid out in a tree data structure. That's how it divides. So you have your HTML tag on the top, then you have a P tag, then you have your other tags. So those, the DOM, they use the tree structure, and that's how they actually divide your HTML. Excellent. All right. So what does the key has? Similar to linked list, it has data, and then it knows. I won't call it node. Well, let's call it node. So it knows what's a left node and what is a right node. And same thing over here. This knows what is the left node over here and what is the right node over here. Left node, right node. Okay. These nodes over here are null. So that's where the key can get started. Okay. Every node in the tree knows what's left of it and what's right of it. Okay, just remember this, just like linked list. And then let's go back to our, let's see if this is here. Binary tree. Remember the binary search tree? Yeah. Okay, now how does a binary tree, first of all, why is it called binary tree? Right? You only have two children or two nodes or two branches. Every node has just two. That's why it's called binary tree. Right? Just to confuse you guys, there are entries also which has multiple children. That's a bit more complicated. Right? Unless you are interviewing for Google or Facebook, then they will ask you about those. But binary tree is a tree with two branches or two nodes. Right? Now, how is your binary search tree created? Right? Is it an array? Eleven, 7. No. Well, I'm trying to create one first. How is this created? 11, like, how do you think this came about? Like, these are not random numbers that they just put over there. Yes. 11, 7. Let's start with it. Let's suppose this is the array that you get 11, 7, 15, 5, 9, 2, 6. I don't know if I'll come to this conclusion, but the concept is still the same. So how the binary search tree is made, a binary tree is made that you take the first element, right now the tree is empty, so this becomes the parent. Okay? Now, this is your point. Every other number that comes in, if it is less than, it's going to be on the left side. If it is greater than 11, it's going to be on the right side. This is true for any binary tree. On the right are the larger elements, on the left are the lesser ones. Okay? Now 7 comes in. 7 is less than 11. So it goes here and creates a tree. Now this is a smaller tree on its own. Any number that is greater than 7 will be on the right. Any number that is greater than less than 7 is going to be over here. Now let's suppose 15 comes in. What happens? Checks with this one, bigger, goes over here. Okay? 5 comes in. What happens? Smaller, it comes over here. But there's already something here. We're going to compare with 7. Now, what less, so it's going to put it over here. Okay? Because once you keep going down, this is a tree is on its own, this is a tree on its own, so it kind of keeps going. Now, let's suppose 9 comes in. Left, right. Left, right. Okay. Number 3. 3 less comes here, less comes here, then okay, and then you keep going. And this is how you build this binary tree. Okay. Now, if you want to search something, how does it work? Let's suppose I want to search 6. Less than, so 6 is never ever going to be over here, right? So you see, why is it faster? In just one instruction, you have like cut down the number of elements that it has to search by half. Right? This is how it is laid out. That's why it's faster, right? Then I come over here, 6, right? It's never going to be on this side, right? Another half. This whole tree is kind of cut off already, right? In just 2 instructions, I have cut out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements, right? So it has to be somewhere over here, all right? Now you come to 5, right? This is cut out. 6 can never be on the left side of this tree. It has to be over here, right? Let's suppose I was searching for, is there a number that is not here? 1. Okay, what about 1? So I come over here, 1 can never be over here, right? It has to be over because it's less than 11. Okay, I'm over here. 7. Can it be on this side? No, it has to be on this side. So it comes over here. 5. Can it be on this side? No, it has to be on this side. 3. Now, can it be, it checks, it says, oh, the roots are, these are called the roots. The next is null, right? So this means there's no 1. That's why it would say, oh, I didn't find 1. And if it reaches the bottom and if it comes, why would it say null? Remember, each node has two things, right? A node is left node and right node. For this case, left and right would be null. So it's going to, if you look at the code for this, later on you will see like checking for null. If it finds null, this means that you have reached the end of the tree. Okay, any questions on binary tree? Everybody understand what a binary tree is and what is a binary search tree, right? You are searching through this tree. Okay. Oh, we'll come to it. All right. There's not a lot of information. Again, this is you see progressively the data structure are getting complex, right? Graphs are super advanced binary trees, right? And they're complex. They are used in your Facebook or any locations and everything that you're trying to do. They're kind of similar to binary tree, that they have nodes and they kind of know which one to go next one. Okay. But again, they are more complex than binary search. They're not as simple as that. They have more nodes and kind of linking. Usually, if you come to a problem, you probably won't. But like you're trying to find like a shortest distance or something between 2 locations, usually it refers to graphs, that you have to come up with an algorithm that kind of is more efficient, and that efficient algorithm is graphs. Okay. As I said, the friend list and Facebook and all that stuff, they're kind of using graphs to kind of link through. That's how they know like how closely you're related, or how your friends are. If you have a second, a third, it's same with linked list, LinkedIn also, right? You see those suggestions that come up. They're kind of using graph to see how far you are out in that graph. Okay, but graphs essentially are kind of advanced binary trees with more nodes and more complex algorithm. Let's see. All right. Any questions? Yes.
If you end up with a binary tree like
Oh.
that, what would it, in the like it refactored would be more convincing, more clear?
Yes. So there's a term called balanced binary tree. What that means is that the number of nodes on each side are kind of same, or at least same. Like this wouldn't be considered a balanced binary tree. A balanced binary tree would be more like if your top was maybe 5, I think. Okay, a balanced binary tree is one that has um, like this. It has nodes that are kind of heavy on both sides. This is more heavy on the left side. Okay, so it won't be considered a balanced binary tree. This would be considered a more balanced. And how do you make this more balanced? Again, this is very advanced stuff. Okay, what do you have to do? You have to kind of shift these elements. Like you have to see how you can make it balanced. So I think looking at it, if you make 5 on the top, if 5 is your parent, then this would be kind of shifted towards more balance. Like these elements will kind of go towards 5 or 7. One of those. What was it? 9?
7 or 9.
7 or 9, yeah. I thought there were 2 more. So you will have to kind of form this tree into this format, and this is called balanced tree. Again, this is a little bit more advanced. Unfortunately, well, if you are looking for really tech companies, they actually ask you to give you this tree and they say, hey, can you make it a balanced tree? They're basically saying, hey, the number of root nodes are kind of same on both sides. Yeah, you can do it. There are different algorithms that you can make it more balanced, and those would be called balanced binary trees. All right, any other questions? So we start with arrays, stacks, queues, linked list, binary trees. What else we saw? Yeah, those are like 4 or 5 ones. So those are more popular data structures that if you're learning a different language, you will see those actually supported over there. All right, any other questions? Good. All right, so here's the interesting part. This is actually officially the last lecture that I will be giving you. Like, this is the end of the lecture. We are on week 22.3. Right? Every cohort, I try my best to make it as easy, or this is already very difficult, right? I hope this is like me asking you guys, and I hope this is the response. Okay, I try my best, but still it is already difficult and it's already confusing. There are some things that cannot be made easy. I don't know. I don't find. I mean, there are different ways, and I try different ways. Hopefully, you guys got benefit out of it. What you guys were looking for, and you guys are better than when you walked in week 1 versus today. But today is officially, this was the last part. There's no lectures. The next 2 weeks are just project weeks. Okay? Let's go to start crying or something else. All right, we made it. There you go.